Okay, so first let's create a data frame that we can work with here. I'm going to create an ND array, one-dimensional ND array A12, np.arange range 12. There we are. Whoop, A12. There we go. And we will shape this. This is only just going to be displayed. It doesn't actually reshape A12 itself. But we want to get a 4-row, 3-column data frame out of this, and we're going to start with this two-dimensional ND array. Okay, so here's another way of creating a data frame, is to simply give a two-dimensional iterable, this two-dimensional ND array in this case. We're saying I'm not gonna type this all in. Let me just copy and paste. So we're going to take our reshaped 4-row, 3-column ND array, and we're going to specify index names and column names rather than accepting the default indexes of 0 through 3 that we would get. All right, so let me copy this thing. Ah, rats. Try again. There we go. And paste it over here. There we go. So now I have my 4-row, 3-column data frame. And we know that I can access an individual column by using the column as a subscript, or since this is a valid identifier, I can also say F2 sub C0. And I can use the .loc if I want to access a row. So F2.loc of R1 gives me that row R1 with the column names used as the labels for this series. Okay, now I can get a Boolean data frame to use as a Boolean index by doing a comparison on values in the data frame. Okay, so F2, well, let's build up to this. So F2 is our 12 values. F2 mod 3 is going to be the remainder after division by 3 of each of these values. And you'll notice that the first column is all zeros. Those are the ones that are evenly divisible by 3. So if I ask for F2 mod 3 is equal to 0, I get trues in the first columns and falses everywhere else. And I can then use that Boolean index. Let me just copy and paste this guy here. So F2 sub, and then my Boolean index, to identify a view on part of this underlying data frame that I want to modify. And in this case, I'm modifying those selected items by multiplying by 2. So I used to have 0, 3, 6, 9 in the first column, and now I have 0, 6, 12, 18. All right, so we have looked at subscripting to access an individual row or an individual column. We've also taken a look at using Boolean indexes to give us a view on certain cells within the data frame. Here we're taking a look at slices. This is using .loc, so we're getting a slice of rows in this case. Here's my F2, and if I ask for F2.loc, now I'm using named labels here, so R0 colon R2 means from R0 up to and including R2. Okay, so not like integer indexes. Named indexes go up to and including. All right, so there we've got R0, 1, and 2. For whatever reason, and I find this a little inconsistent, I tend to avoid it actually, you can just use integer indexes to get rows, and in this case, the meaning is up to but not including. And for whatever reason, I'm not using the .loc here to specify the rows that I want to get. Now, .loc, as we've seen, uses labels. And here I'm accessing an individual row. So f2.loc of the individual row R1. Or if I use slices, f2.loc of the sequence of rows from R0 up to and including R1. And then this third example is using fancy indexes. All right, so we've got slices, we've got Boolean indexes, we've also got fancy indexes, just like we do in ND arrays. So R3, comma, R1, come on, R1, there we go, is going to access row 3 and row 1. So I'm not only able to access individual rows, but I'm also able to change the order of those rows by using the fancy index subscripting. iloc is what I use if I want to use the integer values to access rows. Okay, so f2.iloc 2 gives me row sub 2, which is actually R3. Oh, no, pardon me. Okay. Okay, I've got R on the brain again. Okay, so the rows are labeled R0, 1, R2. So row sub 2 is R2. And so I've got the 12, 7, 8 column. Well, I've got the 12, 7, 8 row displayed as a series. And I can ask for a slice using integer subscripts. This means row sub 1 up to but not including sub 3. So in other words, R1 and R2, but not R0 and not R3. And fancy indexes with iloc. So row sub 3 followed by row sub 2. Okay, so very similar to what we did with ND arrays, but with the annoyance here of having to remember to use loc for named labels and iloc for integer subscripts used alternatively to the named labels. To access individual cells, as we've seen, we can specify a row first and then a comma and then a column. All right, so if we look at F2, F2 sub R1 comma C2 is that 5. And I can use slices and I can use fancy indexes. So f2.loc sub R0 up to and including R2, with the columns C2 first and C0 afterward. All right, so here's all of F2. So I got these 3 rows, R0 up to and including R2, but I got column C2 first, followed by column C0, so 2, 5, 8, and then 0, 6, 12. And then here we have iloc being used with integer subscripts and fancy indexing for both the rows and columns in this case. f2.iloc row 0 followed by 3, and within those rows column 2 sub 2 followed by column sub 0. All right, so in the upper left corner we have row sub 0 column sub 2, all right, which is row sub 0 column sub 2, that value, and so forth for the other 3 values in that resulting data frame. Okay, now, so that pretty well beats to death the various kinds of indexing that you can do to access rows, columns, slices, Boolean subsets, and fancily ordered rows and columns within a data frame. Now we're going to take a look at arithmetic on data frames as opposed to arithmetic on series. We still have this issue of what if you try to add together 2 data frames whose rows and columns are not the same. I've already got F2 here with 0, 1, 2 in the first row, 6, 4, 5 in the second row, and so forth. What I want to do is create a new data frame F3 that's a little bit like F2, but with an extra column and 1 fewer row. So I'm going to get 4 columns and 3 rows for F3. F3 is going to start out as a copy of F2, and then to F3 I'm going to add another column, C3, and this is going to contain odd numbers, 1, 3, 5, 7. All right, so here's F3 now with a 4th column containing 1, 3, 5, 7. Then I'm going to get rid of this row. And remember, I don't use del for rows. I say f3.drop. And that doesn't actually directly drop R1 from F3. What it does is to return to me a copy of F3 in which R1 has been dropped. So I have to assign that back to F3 in order for F3 to be changed. Good, so now I've got F4 that has 4 rows and 3 columns, and I have F3 that has 3 rows and 4 columns, and there is some commonality, but there's also obviously some important differences. If I add these together, F2 plus F3, well, let's see. So F2 doesn't have C3, so I'm going to get a bunch of not numbers for column 3. And F2 does have row R1, but F3 does not, so I'm going to get a bunch of not numbers for row R1 as well. All right, so I've got this whole row of not numbers in row R1 of the sum, and this column of not numbers in column 3. Now, sometimes you would like to be able to use a default value or a sort of a fill value in case a number is missing from one data frame but not the other. For example, maybe I just want to say, all right, look, if a number is missing, then let's just assume that the missing value is equivalent to 0. All right, so we're going to use a fill value of 0 here. And instead of saying F2 plus F3, we're going to say F2 dot add F3. That's the same thing as doing a plus, but we're going to say F2 dot add F3 with a fill value equal to 0. Now, if one value of the sum is missing, so for example here, we've got row R0, but in one of the two data frames we don't have column C3. So we do have column C3 in one of the data frames, but not in the other data frame, and so we added up those values and got not a number. But this time we're going to add 0 for the missing value to get a valid value for C3, R0 sub C3. Similarly, we're going to get valid data or valid results here and down in these two positions. Now, if you take a look at F2 and F3, though, probably I should do that. Let's delete this, and let's remind ourselves what F2 looks like. All right, I've got F3 up here, but let me display it again. All right, so F2 is missing column C3. F3 is missing row R1. Both of them are missing cell R1C3. So R1C3 has no data from either one of these two data frames. So it's not possible to just fill in one of those missing values with 0 and have a good result. In other words, if I say F2 dot add F3 with a fill value equal to 0, for this cell, R1C3, I have no data of any kind, and the data frame add function here refuses to decide that, okay, well, in that case I'll just add 0 to 0 and get 0. No, in that case you're just stuck with a not a number for that. Okay, we can also sort rows and or columns within a data frame using a function called sortIndex. And let me quickly put together this example data frame with a copy and paste. Let's remind ourselves that F2 is this data frame with 4 rows and 3 columns. Notice that I can take F2 and convert F2 into a two-dimensional ND array by using the np.array construction/conversion function on the data frame. All that does is to pluck out the data part of the data frame, ignoring the column names and the row labels, and giving me back a two-dimensional ND array in which the values all have to have the same type. So here the values are all integers, so there's no conversion to do. But if I did have a mixture in here of booleans and strings and floats, let's say, then upcasting would come into play with this conversion. In this case, there's no need to do any upcasting because everything is ints. All right, so what I'm doing is I'm using that ND array stolen from F2 as my data, and I'm giving named indexes and column names. Okay, so I'm gonna index the rows as ADBC and specify the column names as ZXY. The only thing to point out there, which is minor, is that these are not in alphabetical order. All right, so let me copy and paste this thing. Okay, let's try that again. Hey, come here. What's going on? Okay, I did something goofy. Let's try this again. All right. Copy. Paste. Yay, it worked. All right. So here we have F4. Same data that F2 has, but different column names and different row labels. And you'll notice that these things are not ordered. Now, if I would like to order the rows, then I can just invoke the sort index function on that data frame. This does not change F4. What it does is to return to me a copy of F4 in which the rows have been ordered by their labels. So the output that I'm seeing here has the row labels in order A, B, C, D. But F4 itself is still the same. F4 is not changed. All right, now you might think, cool, I can sort the index here by saying sort index. So how about if I say F4 dot sort columns to sort the columns, but no such luck. Instead, we have to have some awareness of sort of the internals of data frames here, which is that the row axis is called axis 1, axis 0, excuse me, and the column axis is called axis 1. So if I say F4 dot sort index with axis equal to 1, notice that 0 is the default. 0 is the default, so we sort rows by default. But if I say axis equals 1, now I'm sorting the columns, so I get X, Y, Z. And now the rows are not changed. If I want to do both things, I can say F4 dot sort index to sort the rows. And I can also do immediately, remember that F4 dot sort index is going to return a new data frame. Well, so F4 dot sort index is a data frame, and therefore I can call sort index on that data frame. And this time I will say axis equal 1. And by doing two sort indexes, once on the rows and then once on the columns, I get A, B, C, D for the rows and X, Y, Z for the columns. In the example on slide 41, rather than getting the rows in ascending order, I'm getting them in descending order. And this is also, I think, a little awkward, but the way you get things in descending order is to use the keyword option, the keyword argument, the keyword parameter, I'll get it right eventually, the keyword parameter ascending set equal to false. So let's get a copy of what I just did there and put in here ascending equal to false. All right, and so now I've got DCBA for the rows and XYZ for the columns. Alrighty, so we have pretty well flogged data frame manipulation to death here. We've seen how to access columns, rows, cells. We've seen how to use slices of columns and rows. We've also talked about using Boolean indexes to access certain subsets of cells within the data frame, and fancy indexes to access certain rows and certain columns, and also potentially change the order of those things. And we've taken a look now at how to sort the indexes in ascending or descending order. In this next part, this is really the last part, we're going to take a look at doing some statistics on data frames. This is going to involve setting our NumPy random seed to a known value 1 so that we get the same sequence of random numbers that are shown on the slide. And we've already seen last week how to get np.random. Rand_n is going to be random numbers from a standard normal distribution. I want a 3 by 3 matrix of these, and I want to round the digits after the decimal place to 3. All right, so there's my data. And I'm going to create a data frame from that. And to avoid typing, I will just copy and paste this code here. All right, so this is a 3 by 3 data frame, 3 rows, 3 columns of numbers drawn from a standard normal distribution. All right, and so I can use vectorized summary statistics to get the sums of each of the columns, to get the means of each of the columns, to get the variance of each of the columns, to get the standard deviation of each of the columns. I can also get a whole bunch of summary statistics by asking for the describe of the data frame. Okay, so there I get the count of the number of records, the number of rows, mean, standard deviation, minimum, maximum, and then the quartiles, 25, 50, and 75% quartiles. And there are a whole variety of additional statistics functions available as well that I'm not gonna pronounce their names aloud here, I guess. Alrighty, so that gets us to the conclusion of what we plan to talk about data frames. And I apologize for being late getting this posted. I hope everybody is well. I hope everybody is keeping safe. And take care. Bye.